Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. Dr. Dave here, and Barney Brown, who's not a scientist, but he is a musician, but he works with the University of Cambridge doing all the webby things and things like that. So, Dr. Dave, what's new in the world of science for you?
Well, the Japanese mission Hayabusa has come back on a rather long and tortuous route, back from visiting an asteroid. It was launched 7 years ago. It went up and visited the asteroid Itokawa, and they're not quite sure, and it should, in theory, have picked up some bits of the asteroid. However, the system they had for picking up bits of the asteroid sort of didn't quite work, but they accidentally crashed it into the asteroid sort of gently, so hopefully it will have picked up some bits of the asteroid. And this week, a little lander from this mission parachuted down into the middle of the Australian desert. And with any luck, in the middle of that lander, there should be a few tiny bits of asteroid. But nobody knows until they open it up.
There's something scientific. Nobody knows.
Well, not for a few months. They've probably got an incredibly careful system for opening it up and cleaning the outside so it doesn't get contaminated by dirt from the Australian desert, because that would completely ruin all their results. So it's going to take them a while to open it up. Hopefully in a few months' time they will find out what the asteroid was made of and actually have some bits of asteroid sitting around.
Let's go to the text and say hello to Kay in Cambridge. And they ask, Dr. Dave, how does vinegar cook egg? Dave.
OK, the first thing is what you mean by cooking the egg. What happens when you cook egg is there's lots of proteins in the egg white. Normally they're quite grouped up in fairly small lumps. And when you heat them up, they shake around, they've got lots of energy, they change their shape, they tend to tangle up, and so they become much more, so they all tangle up, and so instead of being something which will flow in a kind of viscous way, it actually turns into a jelly. So cooked egg white is a jelly. And this process of denaturing these proteins and changing the pH, so making it very acid, will do something very similar. You can also do something very similar by making it very, very cold. If you put an egg on liquid nitrogen, it looks like it's cooked. It hasn't actually cooked, but the same thing has happened to something very similar has happened to the proteins in the egg white. So yeah, it's just doing something similar to the proteins.
All right, let's go to our next one, which comes in by email, and this is from Simon Chu. You love The Naked Scientist and you're a great fan of the podcast. He asks, does the moon's orbit decay?
OK, so normal satellites, they're orbiting around and slowly they'll lose energy because they'll bump into the odd bit of few gas molecules, because the atmosphere is very, very tenuous, but it does just about exist out, especially where the low Earth orbit satellites are. And that applies a drag to them, and so they lose energy and they spiral down towards the Earth. So the first thing with the moon is it's a lot higher than virtually any of the satellites. Most of the sort of satellites which drop out of orbit very quickly are only a couple hundred kilometres up. The sort of satellite TV satellites are about 36,000 miles up. But I think the moon is, 360,000 kilometres. So,
no good asking me, Dave, I know nothing.
A lot higher up, at least 10 times higher up. So there's a lot less... There's a lot less gases up there, so there's much less drag on it for a start. Also, it's moving slower, and it's a lot heavier, so the drag will be less because the drag is proportional to the surface area of an object. Because the moon is so big, its mass goes up faster than its surface area, so the drag for a start is a much smaller effect. And so actually, though, the orbit is increasing; it's not decaying, and the reason for that is the tides. Because what the moon is doing is it's applying a drag force on the water on the Earth, which is creating these tides. And that's slowing down the Earth's rotation very slowly. In fact, there used to be 400 days in a year 200 million years ago. They found this by looking at little layers inside corals. There used to be 400 days in a year, but the Earth's rotation is slowing down very slowly. And as you're slowing down the Earth, the moon is actually getting speeded up, it's gaining energy. So the moon's orbit is actually increasing with time, very slowly rather than decaying.
All right, let's go to the phones next and say hello to Mark. Hello, Mark in Dunstable.
Hello, Sue.com.
You're through to Dr. Dave. What's
Hello,
your question?
Dr. Dave.
Hello.
Dr. Dave, I must admit, every time I hear the CERN machine, I'm sorry, I can't remember. No, it's
Large Hadron
accelerator.
Collider.
Yeah, the collider. Every time I hear it goes bang and it's failed, this thing freaks me right out. But nobody's ever been through a black hole.
The argument against that one, which I think is quite a good argument, is that actually the energies of collision which the Large Hadron Collider is creating, although they're very far larger than we've managed on Earth by man as created before, there are actually things called cosmic rays, little particles crashing into the atmosphere all the time, sort of protons or little atomic nuclei, and they're crashing into the Earth's atmosphere, some of them with sort of 10 a day or something, with energies 1,000 times or 1,000,000 times greater than what the LHC is creating. I think there's a fairly good argument that in 5 billion years these haven't caused the Earth to collapse. We're very unlikely to be able to do it in 20 years with the LHC with something much less energetic.
Yeah, so don't you worry about it, Mark, all right?
No, I'll have a peaceful night.
Take care.
Yeah, bye-bye.
Bye-bye. This one here from Mike. Yes, Mike has asked, and maybe Barney might be able to help with this one as well. He's asking, how does Google stay on top of all the information going around on the internet? Good question. You going to hand this one over? Or do you know?
I can have a crack at starting it off, and maybe you can jump in when I start going into the areas of bad science.
I'll do my best.
Well, Google uses things called spiders, which are small programs which go to loads and millions of websites and then follow all the links on those websites and keep on following those links again and again and again and again and again, spidering around the web and then storing a massive database with basic information about all of the different web pages that those spiders have found. So. Yeah,
they do it by being A, very clever, and B, having a huge number of computers. I think the numbers I've seen for it, they reckon they've got over 1 million computers in various data centres. Basically, they've then managed to glue these together in a very clever way, so that if one of them explodes, then the other ones just take over the work immediately, and you, as a user, don't notice at all. And they have computers breaking all the time, and their network they've built sort of just works out this one's broken, we'll ignore that one and just use other computers in the rack. And yeah, they've just got an immense number of computers. I think they store most of the information in memory, so they don't. So not very much is on the hard disks. They kind of cache it all in memory, so it's very, very quick retrieving the data.
Now then, a question here from Pamal Ki, who must be in some weird and wonderful country in Lovely, but he says, this is too complex for the science teacher to understand. Are colours really representative of reality?
That is a very interesting question. It's actually quite a deep question. I mean, basically, the colours you experience, all they're telling you is you've got 3 different types of cells in the back of your eye.
Yep.
You've got cones which are called red cones, green cones and blue cones. When light shines on those, they get excited, and the red cones get slightly more excited with red light. The green cones get slightly more excited with green light, and the blue cones get more excited with blue light. In fact, different people can have slightly different cones. I think there's 2 different green cones which have a different response, different frequencies. So some people actually see yellows differently to everybody else. You can have 2 boxes which to me looked exactly the same colour, but I was at a lecture and there was someone else in the lecture who reckoned that they looked definitely very different colours of yellow, because they're made of mixtures of other colours, and their eyes don't work the same as mine do. So colours are kind of an approximation to something real, because light has got lots of different wavelengths, and different wavelengths we associate with colours. But it's a very, very rough approximation. In fact, there's an infinite number of different wavelengths, and our eyes basically compress that all down into 3 channels, sort of reddish colours, bluish colours and greenish colours. And there's a huge amount more information there which we can't see. Other animals can see other colours completely. Things like bees can see into the ultraviolet, which we can't see at all. Also, things like birds have got a much more complicated form of colour vision than we have. For a start, they've got 4 different kinds of cells in their eyes, and some of their cells, these cells have got little bits of coloured oil in front of them, so they can probably distinguish. Instead of just 3 channels like we've got, they've probably got 7 or 8 or 9 different channels, which is could be very useful for identifying different bits of foliage and whether fruit is ripe and things like that. So it's a huge approximation, and it's not always the same between different people. And of course, you get colourblind people who, instead of having 3 blue colourblind people, instead of having 3 different channels, they only have reddish, greenish, and bluish. So they've only got 2 channels, so they see the world in a completely different way. So it's a huge approximation.
What did you think, Barney?
Well, I'm colourblind, which means I'm terrible at picking strawberries, for example.
It's very hard. Yeah, I mean, it's thought that because most mammals are red-green colourblind, and it's just primates. I think it might have been evolved somewhere else who have evolved this third cone basically to be able to tell when fruit is ripe.
Does that mean there are any benefits for being red-green colourblind?
Not that I know of.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. We were talking earlier about the drone of the, the horns, the World Cup horns.
Vuvuzelas.
Yeah, vuvuzelas. Why is it that they're coming out with that frequency? Because it's a kind of own tone, if you like, isn't it? Because there's nothing really in it that makes the particular note.
I mean, it's the size and shape of the object. I mean, it's things like big trumpets tend to make lower notes, whereas a small, little, tiny, short trumpet will make a higher note. It's to do with air resonating. And if you've got a very long distance for it to resonate in, it's got more time and everything will happen slower, and the slow vibration is a low pitch. Very short, everything happens much quicker and you have a much higher pitch. And so it's just the shape of the vuvuzela. If you made it a different shape, it would come out a different sound.
Now, let's go to our questions over here now. Fearless Frank from Felixstowe has an ordinary house with domestic central heating. The tank where the hot water is stored usually in the loft. Would the water be safe to drink, keeping in mind of Legionnaire's disease?
Water will go off after not very long. I mean, the only reason why water that you get out of the tap is safe to drink for a few days is that it's actually got very weak, essentially bleach in it. It's got chlorine in it, and that will kill any bacteria in there. And I mean, that saved millions of lives worldwide. People used to die of all sorts of hideous waterborne diseases, things like cholera. And as soon as that chlorine basically leaves the water, it will slowly evaporate off after a couple of days. Then the water will go off and all sorts of things can grow in it. And so I certainly wouldn't recommend drinking it, certainly not if anything can get in there. I mean, it depends. If you boiled it, and if not, certainly not the central heating water, which is going round the central heating loop, because that's got lots of poisons in it to stop things growing in it again. But water which has been sitting in a tank for a while, if you boil it, then you'd kill off any bugs, and it should be relatively safe to drink. But certainly avoid anything with any of the nasty sort of the things which stop your radiators going rusty, and things which stop bugs growing in it, which killed off an area of grass on my garden for about 2 years once.
Did it?
So there's some quite nasty things in there.
Let's go to the email here, and this is from Mr. Freeman. Very formal. Hello, Mr. Freeman. Why are green lasers visible at night?
In theory, you shouldn't be able to see a laser if the air was perfectly clean. The laser would just go straight through. The light carries on in a straight line. If light is going in a straight line and not hitting your eye, you can't see it because you only see light which has hit your eye. You tend to be able, where you can see a laser if there's something in the air, so a little bit of dust or a little bit of moisture particles, so little droplets of water, something like that. It hits those, it bounces off, some of it bounces into your eyes, and you can see it. So if you look quite closely, you'll either see smoke or you can see little particles of dust. Green lasers tend to bounce off smaller particles of dust than red lasers, for the same reason that red light will go through a lot more atmosphere at the sunset, because bluish and greenish colours tend to bounce out much earlier than red. So if you look at a sunset when the light is going through, it's just skimming through a large amount of atmosphere, all of the green and blue light has bounced off, and the red light carries on all the way to your eyes. So if you're using a green laser of the same power, it will tend to scatter off more dust than a red laser would do. But most of the reason why these quite often happen is that the lasers which people are using to point up into the sky are actually just very powerful and actually quite dangerous. I've seen a few of these you can buy off the internet, and they could quite possibly blind someone without too much difficulty. So be careful.
Another one on the email here, which has come from Derek, who says, we can see in the dark using infrared technology. Apart from dodgy X-rays and other damaging stuff, what other spectrums might we use with benefit?
The astronomers are using all sorts of bits of the spectrum. One region of the spectrum which people are quite interested in at the moment is the millimetre waves. This is the region in between infrared light and microwaves, so the sort of things which radars use. So for a start, we're already using radars in order to be able to look a long distance using radio waves, and then you can see ships and planes and things very effectively. Millimetre waves have got a bit better resolution than that. They're reflected off your anything which conducts, so your skin conducts well enough, but your clothes don't conduct well enough to block it. So a lot of anti-terrorist people think it's a good way of seeing things like guns under clothing. It has caused a load of slightly interesting privacy issues, because essentially you can see people with their clothes off. Not any detail, not very good detail, but you can see the shape of people with their clothes off. Astronomers see all sorts of interesting things in the ultraviolet and X-rays. So basically, we're using most of the spectrum for in order to see, and of course we're using the radio, large region of the radio spectrum, which is another colour of light, for you to listen to me now on radios and mobile phones and all sorts of things like that.
One here from Mike in Yarmouth. He says, a friend at work recently went to the Galapagos Islands, where they have the Komodo dragons and giant tortoises. The Komodo dragons can swim, so I understand how they got there. However, do the giant tortoises get there? Do they also swim?
I think when they got there, they weren't nearly so giant. They were probably quite a small, conventional-sized tortoise. And it's quite possible for one of those to get stuck on maybe there's a flood somewhere in South America. Tortoise sort of grabs hold of a bit of a tree trunk, and then it slowly floats out into the middle of the ocean. Tortoises have got a very slow metabolism, so it could probably survive like that for months. And then eventually, if this log gets washed ashore on the Galapagos Islands, then you have a tortoise there. As soon as you get two tortoises, then they'll breed and you'll get lots of tortoises. And if there's an advantage for being a large tortoise, then slowly over millions of years the tortoises will evolve to be bigger and bigger and bigger until you get the giant tortoises.
All right, I think we've got time for one more here on the email, Dave. This comes from Kirsten Olsen, saying that they recently watched the BBC TV show Survivors, which chronicles the aftermath of a global flu-like pandemic that wiped out 90% of the Earth's population. So they ask, how would decomposition gases affect the atmosphere?
I think this is, if a huge number of people die, would it affect the atmosphere very much? The answer is probably not very much, because if you've got 5 billion people, then how much do they weigh? That's going to, if everyone weighs 50 kilos, so that's about 250 billion kilograms, so about 250 million tons of people, which sounds quite a lot, but that's still far less than we're burning every year. I mean, every person in the world in the UK is burning about 12 tons of carbon. And although methane is much worse greenhouse gas, actually nowhere near that amount of people would be decomposing to form methane. Most of the decomposition will be to form carbon dioxide. And probably actually if you have fewer people, then trees will start to grow. So on average, I think probably the atmosphere would be a lot healthier if most of the people died, which is rather depressing.
Let's go to the phones now. Hello to Paul in Braintree. Hello, Paul.
Hello there.
Hello there. You're through to Dr. Dave. What's your question?
If you're viewing the Earth from space,
yeah,
then you can see the sun the light from the sun is actually bending around the back of the Earth slightly. So how does gravity bend the wavelength of light?
Okay, gravity will bend light very slightly. I expect if you can see it, the effect on the Earth is very tiny, so I expect if you can see it, the effect is more likely to be the atmosphere, because the atmosphere acts a bit like a prism and will bend light around a corner for a bit. In fact, when the sun is setting, actually, when you see it dropping below the horizon, is actually significantly after when it actually drops below the horizon because of this bending effect. But saying that, gravity does bend light very slightly. The way Einstein thought of it, because he was the one who worked this out in the first place, was that basically gravity bends space itself. So light is going in a straight line, but space is bent. And so if you've got something very heavy, it distorts space in such a way that, although from the outside it looks like light is going around a corner, in a more fundamental way, light is going in a straight line. It's just that space is bent, so it ends up going in a slightly different direction to the way you'd expect, if that makes any sense at all. If you imagine a sheet, a rubber sheet, and if you've got something heavy on that rubber sheet, the rubber sheet gets deformed, gets bent.
Stretches.
Stretches.
I've seen this demonstration.
Yeah. Now, if you imagine you're an ant trying to walk in a straight line, because space has been deformed and bent, although you would always think you were walking in a straight line, you would actually end up going around a corner as a result of gravity. If you put a wave over this rubber sheet, it would also get bent.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.